Okay, I've started recording. Please share my screen. Okay, I guess you can see my screen, right? Okay, so this is week 11, right? And yeah, so in week 10, what we did, we uh, give you a kind of quick introduction to reinforcement learning, right? And then also we discussed Markov processes like Markov process, Markov reward process, and Markov decision process, right? And also we covered three key concepts known as return, value, and policy. Okay, so what we will do, and today our objective would be to go into these two topics. So we have like briefly introduced the, I guess we are recording it, right? Yeah, we have started recording. So we have our like earlier our we have briefly introduced the Gridworld framework, right, to you so that you can test things out, test algorithms out. So and we also did this policy evaluation algorithm. Maybe we'll touch upon them once, okay, just to give you a kind of like revisit to those concepts, and then we will go for another method known as policy value iteration and then policy iteration. Okay, so that would be our kind of goal today. Let me open up the code window. Yeah. Okay, we have the code window. Okay, copy, name it week 11, right? So let's just quickly remember what we did last week, right? So Markov process, what was it? It has possible states, right? A starting state and then a transition matrix from any state to any state, right? So it's basically an NFA type structure, finite automata, non-deterministic finite automata type structure that has this transition probability matrix has probability of transitioning from any state, let's say S1 to S2, right? So if there are, let's say, n possible states, then it's an n cross n matrix. Now transition functions is nothing but from one state, how we do transition to the next state. You just like you have the one hot representation of the initial state, you multiply it with the transition matrix, and then you sample the next state, right? That was the entire transition method. So you can kind of abstract it. There is a transition function given the current state and the probability matrix, it can give you the next state. Okay. Okay, and then if you just do this transition time and again, you get a sequence of states that give you a Markov chain. Okay, so this is Markov process. Fine. Now, what is Markov reward process? So it's, and these are very crucial for your MCQs. So there can be like like if there can be this type of questions, and you have to mark which type of process it is: Markov process, MDP, MRP, or MP. Okay. Now, Markov reward process, every state has a associated reward. That's it. So everything is same. Only where you reach, right? Based on that state, you emit a reward. That's it. Now, because of the reward, there can be multiple like concepts built on top of it, right? One is this value of state, value, reward, and so reward immediately gives you another concept called return, and then return gives you value. I guess you have already know these concepts because earlier we derived, right, how these value equations are coming or return equations are coming. So basically return is sum of all the rewards you get from any state. So return of a state S0 means after S reaching S0, how much reward you accumulate to the end of the Markov chain, right, or end of the episode, you can say. Now, what is value? So you can, from a particular state, you can have multiple possible trajectories, right? Multiple possible Markov chains, right? So if you just take a probabilistic average across those Markov chain, that's give you the value, right? So on average, how much is the return from a particular state? That's what is called as value, right? And then we also So so yeah, something like this. You can have multiple possible return values from a state. You just take average, that then you get a value, right? Now, so what was the like in terms of goodness, how we can quantify this type of values, right? This reward is greedy, so you guys look into only one step, right? And then return is like based on the gamma value, right? Based on the gamma value, you can consider it is like kind of future proof, right, or future planned. But it can vary a lot, right? It can vary a lot based on which chain you are seeing, which Markov chain you are seeing. So yeah, so it's basically total reward from a state to the end of the episode or the in Markov chain, but it can vary a lot, right? So that's why you take a average of those all possible returns from a state that gives you value of that state. Now, based on that principle, what we did, we have this equation, right? Let me open up that equation too. Just remember it. Week 10, not lecture 3, lecture 2. Yeah, yeah. You can do a recursive equation like this, right? So value of state is equal to reward plus gamma times PV, and just so that you can also do a direct kind of closed form, that V equal to I minus gamma P inverse R, by which you can estimate value of each state. And because of this, and now just to remind you a bit, so you can compute a value, compute value from P, gamma, all those. So if I only know gamma, P and R, those matrices, gamma is a scalar, right? Then I can compute the value like this. Yeah. So now what was Markov decision process? So in that case, a action component is also there, right? So every state has a possible set of actions that you can take. Based on that action, you can move to any other state and get a reward, right? So uh, your uh, I guess, so you can kind of think your transition matrix to be S cross A cross S. So S number of state cross number of action cross number of state. This is the transition probability matrix. And your reward matrix is S cross A. So it depends on the current state and which action you took, right? It can, so based on the formulation, it can also consider the next state. So the reward can be also S A S prime. Okay. Okay. So from that notion, we like earlier we observed that what we observed. Yeah, so these are the Markov decision process formulation we did last week, right? A and A, you can have two different transition probability matrix based on the action instead, because now action also came into picture. And yeah, and if you know like what action you will take at each state, that entire strategy, right? It is called policy. So at which state, what action will be taken? So here there is this P of ATA. That means it's a probabilistic policy. It's not a deterministic policy. So policies can be of two types, probabilistic and deterministic. If you have probability of taking between a set of actions, that's a probabilistic policy, which is written like this: P of A given S is equal to P of AT by ST. Okay. And it can be also deterministic. So in that case, you had basically a table, lookup table, that okay, state 1 I will take state 3 I will take action 2 with 100% probability, right? So that's a deterministic policy. But anyway, so by that rule, if I just multiply the reward matrix with the policy, you get RT, because the actions are defined in that case, right? So my MDP can be directly converted to an MRP by just defining the actions based on a policy, right? So policy, you can think of it as a lookup table, that which state I will take which action. So my Markov decision process can be directly converted to a Markov reward process. Okay, just look into these equations, right? You can just multiply the reward matrix with the policy. It will give you the reward per state, because the actions are fixed, right? Now, similarly, the transition probability matrix can be also multiplied, and you get the transition matrix. Now, because the state actions are defined, the state transitions will be also defined, right? You are not choosing between actions anymore. You define that, okay, I will take action one all the times. Now by this law you can, or by this rule you can kind of cast Markov decision process into Markov reward processes. And earlier we can compute value, this this value, right, by this equation for a Markov reward process. Now based on this understanding we can actually order policies. Okay, whichever policy has the highest value, I will take that policy, right? That's what we did last week. So if I just looked into the code, see, this is what we did, right? We kind of, from a small grid world, and grid world is what you can kind of create a kind of small mouse finding a cheese through a maze game, right? We can increase it today. Let's see. And now based on this these options, left equal to 2, r equal right equal to 0, up equal to 3, and down equal to 1. These are the numerical representation of the actions that you can take. Based on these actions, we can kind of loop through all the policies, get the corresponding Markov reward process, and evaluate its value. And whichever have the maximum value, that would be my best policy, right? That's what we took. So for a map, for a world like this, let's run that. Uh, yeah. So env dot play as human. Yeah. So for a world like this, what will be the my kind of optimal reward, optimal policy? Should be down and then right to reach the cheese. If I just go right, then I die, right? Because that's a spike there. Okay, it's a spike, so I die basically here. Now the optimal policy is left, sorry, down and then right. That what should be found. That what we should found. Okay? Yeah. So, but you can have lots of possible policies, right? So, what are the number of possible policies for your is combination? Yeah, these are the all possible actions that you can take from each state. So, what is the shape? How many policies are there? There are 256 policies, right? So, among those 256 policy, whichever policy has the maximum value that I can take. So, what we are doing, we are looping through all the possible policies pi I, right? Getting the MRP from that and using that equation, right? That equation, uh, see, it's that equation, I minus gamma p inverse, sorry, inverse r, right? This equation gives you an kind of a vector of values for all states, and then just to make it as a scalar quantity, we are taking mean. So average value, whichever policy has average value maximum, that I will take. So dot mean will basically give you average across all state, average state value, right? And then you append that scalar value. Based on that, you just order, okay, 80th policy has the maximum value of 974.74 per state. So I will take that policy. And what is that policy? You can just open up that policy, right? Open up that policy, optimal policy. This is this one. And if I just print this policy, right here, I can also print that on the GUI. Yeah. So it will be something like this. So from the first state, you take it down, and then from the second state, you take a right. This is the, so you must just loop through all the policies. You kind of get this type of graph, and around 80th, that means this peak has the maximum value. So what is the drawback in this case? And this is the entire thing kind of we just revisited from the last week, that we basically traverse through all the possible policies and then get this peak, right? And this is not always possible. So let's see what happens if I have more states. So let's just change our world, right? So our world can be little bit more big. Let's just take from GitHub, from one of my great world examples, and then library. let's just take ENV, yeah, here, right? We can take this world. This is like a pretty small world, not that much big. But let's see how many possible policies are there, even if it is this small. Currently, it is like this, so we can easily traverse through 256 policies with a current machine, right? Say new generation laptop. But let's see what happens with uh, this world. Yeah, if my world is this, so how it would look? Play as human. So it looks like this, right? Now, this is a fairly small environment, right? We can by looking into it, we can say, okay, now this should be my kind of optimal policy to reach the cheese, right? But let's see how many possible policies are possible in this case. Oh, sorry. Yeah. So my actions are this, and how many states we have? Let's see. Uh, NV dot state count, right? So this many possible states we have, 95 states we have, that we have to kind of understand the which action I should take. So what is the number of possible policies? I just combine repeat for number of states, right? So all possible policies with all those four values for 95 combinations. And let's see. Okay, it's taking very long, right? So it's actually 99. I don't think it will. I don't think we can compute it here. It is uh, you can take four values, right? In any four values at any four those states. So 4 to the power 95 would be the number of possible states, right? 4 to the power, sorry, to the power. Yeah, so this is the number of possible states. So that's why I reload, because I know that if I just keep it running, then my entire memory will be hogged and my call will be disconnected. Okay, that's why I just interrupt it in between. So how many possible policies are there? And see what will be the storage, like how much storage I would need. So 4 to the power 95 would be the number of possible policies. And now let's say in Python, one integer is stored at 32 bits, right? So four integers per policy. So this times four integers, 4 times 32, it this many bits divided by, you can just do a bracket, divide by its bits. So now we have to convert it to GB. Okay, so bits to bytes times kilobytes times megabytes times gigabytes, right? Yeah, this much gigabyte I would need. 2.3 into 10 to the power 43 to store the number of possible policies just for this small environment. Where is the environment? Yeah, let me just run it again. Oh, sorry. Yeah, yeah, yeah. Just for this small environment, I need this much GB of, just write it here. Yeah, so the combinations would need around this GB of RAM to load, which is not possible, right? Yeah. So e to the power 43 means it is actually 10 to the power 10 to the power 49. It's very big. It's not possible. Now, what would be the like how we can solve it efficiently? Instead of looping through, you get the problem, right? You get why we cannot go with generating all possible policies just for a small environment like 95 state environment, and compute all possible policies that we can have. We cannot compute it. It's the combination becomes kind of large very quickly. Okay, even if I have 10 states, my combination would be 4 to the power 10, right? So 4 to the power 10, how much is it? So right, 4 to the power 10, it's this much. right? And so how much would I need to store times 4? So let's just copy it from here. Yeah. So would need okay, we can do for 10 states at least. For 10 states we can store it within 0.01 GB. So we can easily get all the combinations and see. So for this one we had 4 states, right? Let me do for a 10 state. Then we can how is the state for this? Okay, state count was 4 for this, right? We can just increase the number of states. While hmm, so how many states currently we have? If this is coal, we have step 7, fine. So this can be coal, and we have a wall here, right? Now we have 8 states at this point. Now we can grow to another level. Cool. Yeah, now we have 10 states, and let's see what is the environment. Yeah, my environment looks like this. So, so my optimal policy goes through the dead select the state where it will be dead. So it's not a valid environment. Let's just changed it a bit. So obstacle should we can put the obstacle around here, right? Yeah. So at the bottom. So obstacle you can put it around here. Now my world would look like this. Now I have a kind of optimal policy to reach, right? Now let's just loop through all the policies then. My state count is also 10. Fine. And see how much memory I would need. I would need 0.1 GB of memory to load all the possible policies, right? So let's not run it. Iteration tools. Yeah, it can store it, right? And what is the length of the sorry combinations dot shape? Yeah, this is the number of possible policies, like same as we computed. Same, where is it? Yeah, 4 to the power 10. This is this one. Now let's just loop through and let's see how much time it would take for us to compute all possible values for all these things, right? So possible policies, okay. So we need state count env dot state count plus env dot state count I, right? And we are taking gamma to be 0.9. Okay. So if I just loop through, and there is this library called tqdm. Okay, import tqdm. Oh, from tqdm import tqdm, and if I just do tqdm here, it will give you a kind of nice bar, okay, progress bar. So run. Now see, it is actually looping through all the possible policies. I see this is the number of policies we are currently traversing, 8, 9, something like this. it would take around 2 minutes to 2 minutes, or it's actually very fluctuating a bit, but it'll take some time, right? So for a small environment like 10 state, we can do it with my machine, like having 8 GB of RAM, right? But if it becomes let's say 95 state, right? And now we cannot store it. But let's say, see whether we can find the best policy with this 10 state environment. Still running. It took 51 seconds till now. We crossed 58%. 53. Okay. Almost done, but it takes a lot of time, right? It takes for a small environment like that, it should be like instantly computed. So the algorithm will learn next will compute it very fast. So it takes around 2.01 minutes to compute, right? And the maximum value that we get is 809.81. What is the index of that value? Yes, we make this here. So the index is, this is the index of the optimal policy we have, right? I'll just replace this part with here, or just replace it with here, right? Here, okay. Now we can, our optimal policy is this, yeah, based on the, where is it? Yeah, here is the mapping of the actions, right? You can see which actions we are taking per state based on the numbers, right? And then you can also print this policy with on top, or overlay this policy on top of the GUI. So let's see. Yeah, this is my optimal policy. Now see how it is optimal. From first state we are taking right, then down, down, left, down, down, right. And if I am spawned here, then my move is up. You got the thing, right? We can compute value functions for all possible policies and then kind of loop through all of them. The problem is we cannot store it for environments which has more number of states, and it will take infinite, like kind of huge memory and computation resources to loop through all of them. So the idea is, if is there is any way, and let's see what is the kind of value that we get over time. So this is the kind of value function that we get over time. If I, instead of, and there is lot of possible values, right? It's like length is 10,000 or something. Yeah, not 10,000. It's like 10 lakh something. These many possible combinations are there. So if I just looked into first 10,000, first 1,000 X limit to be 0 to 1,000, first 1,000 policies, right? They kind of vary like randomly. They kind of vary within minus 400 to plus 400 in a random fashion, right? Now, the next algorithm that we will learn is how we can improve monotonically. So let's say I initialize to I initialize to a bad point. Let's say I initialize to minus 600, right? Now my best policy value is 809, this 809. Now instead of randomly jumping across the value function, is there is any way so that we can improve it monotonically? So in the next iteration, I should have a value function that is more than the previous one, and it should be a kind of monotonic improvement, right? Then I can reach the maximum marks quite easily, or quite kind of in an optimal way. That's what is our next algorithm, okay, which is known as value iteration. So let me just go over the algorithm once. Let me just look through. Yeah, these things you can, these notes and everything are already in that drive folder. Okay, so you can just look into it if you want. Yes, these things you already know that you can compute v with this that we, okay, value. Yeah, this part is also known to you, how to define a Markov decision process. This is, if I add policy with the MDP, it becomes an MRP. Fine. Policy evaluation, fine. MDP control. Uh, okay, so we can actually do it in two ways. Okay. Hmm. So one is this policy iteration and value iteration. So value iteration is actually more efficient. So you'll directly go to value iteration. And to do that, we have to know a thing called Q function or state action value function. Let me just connect my tablet. And it's like really important algorithm that we have uh, and used in lot of places like Q learning and everything is depends on this algorithm. Okay, just connect the graphics card. So why we skipped value iteration, policy iteration, right? So policy iteration means instead of improving the value function, you try improving the policy, next policy. Okay. And there are certain cases that if I go with policy improvement, my value function can get stuck. Okay. And because value function gets stuck, I cannot improve to the next policy. Okay. Yeah. So that's one bottleneck that we have for like policy iteration. So this algorithm is kind of a bit suboptimal. So that's why we're directly going to the next algorithm called, yeah. Yeah, so this is the algorithm. Let me explain you this. Okay, so there is what is the kind of theoretical concepts that we know now. So there is this concept of reward at particular step, small rt reward, right? And then you have return, capital RT, at a particular state ST, right? That is basically sum of rewards from that step to the end of time, right? T plus 1 dot 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 capital R capital T. Capital T is the kind of end of time or end of the Markov chain, right? And then you just multiply it with gamma, gamma 2, gamma to the power T minus T uh, to all the kind of, here you have gamma to the power 2, right? All those things just to kind of discount the future rewards. So it kind of it kind of bounds how future you can look. Okay, so for example, gamma, if it is 0.9, that means you are looking for next 10 steps, and the formula is 1 minus 1 minus gamma. This is the formula how much you can look into future while considering gamma equal to 0.9. It is 0.1, it becomes 10, right? If it is 0.99, it becomes 100. Okay, now then you have this value function VT, and these are very crucial for your like your MCQs. Okay, value function of a state ST is basically average of, so it's called expectation means probabilistic average of multiple trajectories from RT, so at TST, right? So you take average of multiple returns from a particular state, and there can be from one state there can be lot of possible trajectories to reach the end state, right? It might reach to the same end state, it might reach to other end states also, right? Yeah, so that's why you take a probabilistic average. Okay, these are the previous concepts. Now, because the action came into picture, now one state, let's say S, right? S, you can take action A1 or A2, and then based on that state, you can basically go to the next possible states, right? Yeah. So um, you're taking action A1 or you are taking action A2, A1 or A2. Based on that, you are taking some trajectory moves future. In future, you are taking kind of a like all possible trajectories here, all possible trajectories here, right? So you get a total reward. So let's say this is S dash and this is S double dash, right? So you get some reward here too. Let's say R1, and then all this entire part gets some total reward, right? So this Q function is easy to realize. So from one state to the next, if you take an action A1, what is the value you get? Value of S given A1, okay? And then Q of S comma A2, wait, plus two, plus two, plus one. No problem. And then you take value of S on A2, right? So it's basically the same thing, but earlier you have, because there is no actions, right? You can kind of only take average across the returns. Here you have actions, it's basically conditioned on action. If you take this action, what is the average value you get? If you take A2 action on that state, then what is the average value you get? Okay, so your value function can be written like this. It is actually probability of taking A1 given S times Q SA is A1 plus probability of um, A2 given S Q S A2. So it's basically, you can also write it by like by mathematical term. You will see this term in many places. It should be like this: expectation over policy of QSSA, right? Expectation over policy of QSA is actually value of S. Okay, so you basically take probabilistic average across the policy of the Q function, you get the value function. Okay, so Q function is nothing but what is the value function if you take action A1, what is the value function if you take action A2, and you can define it as a table like this for all possible state. If you know the possible states and possible actions, let's say there are S1, S2, S3, S4, four states and two action A1 and A2. So it's a basically 4 by 2, like 4 by 2 matrix, right? But how much value you observe at each state. Yeah. And see, by, so if I have a optimal value, right? Earlier, what we are doing, we are looping through all the possible policies, and then we are taking whichever policy, whichever value has the maximum value corresponding to that policy is the optimal policy, right? So you loop through all policies, take maximum value, and from that you take optimal policy. That was the previous approach, optimal pi. But here you see, from the Q function we can derive pi actually. If I just make this Q function optimal, right? If I have an optimal Q function that from state A1, S1, I take action A1, I have this much value. From a state A1, state 1, I have action A2, I have this much value. So if I know that this value is 10 and this value is 15, I would definitely prefer taking A2 at S1, right? Similarly, if I have let's say 20 here and 5 here, right? I will definitely prefer taking action A1 at state 2. Similarly, let's say this is 100, this is 101, right? And this is, let's say 5, this is, let's say 1000. So I will rather take this action here and I rather take this action here. So from this queue function, I can just take argmax, right? Argmax across this axis. So whichever argument has the maximum value, right? Across this column axis, right? Argmax across column, or you can say argmax across set A, set action set of the QSA would give you 5. And this pi is not probabilistic, right? It's deterministic pi. And why I'm saying deterministic, just do this example. If I just take argmax of this Q function, my policy would look like for S1 it is A2, for S2 it is A1, for S3 it is A2, and the last state S4 it is A2. See, it is kind of a deterministic policy, right? Which state I will take which action. It's not like a probability that, okay, with 50% chance I will take A1, or 50% chance I will take A2 for state 1, for 50% chance I can, and how we can compute probabilistic policies with it? We can just take an Boltzmann function on this, right? This e to the power beta x divided by summation of e to the power all, like beta x1 plus beta x2 plus beta x3, right? Or basically the softmax activation on this. All the Boltzmann, both are same. Boltzmann has the beta component extra. So you just do an Boltzmann operator upon this and you will get a probabilistic policy. Or you can think of it as e to the power x divided by summation of e to the power x over action set A, right? For all values of x belongs to action set A. So this is the softmax optimization also, softmax activation also. And by this you can kind of compute a probabilistic policy also. So for example, it could be, if the shape should be same. So for 10 and 15, we can say it should be 0.4 and 0.6, right? With 40% probability you would take action 1, with 60% probability you will take action 2. But here for policy iteration, sorry, for value iteration, we are not like kind of considering this probabilistic policy. We are considering deterministic policy. Okay. Now let's see the algorithm. You now know what is Q function, right? Okay. So state action value function is something like this. So like Q pi of SA. So what is this equation? See how we can write this, right? How we can write this equation. So there is this state called S. You take action A1 or you take action A2, right? And then based on that, you kind of follow a policy pi. Next, you follow a policy pi. Okay. And then everything you get from here. Let's say this is S prime, and here it is also S prime, right? You take another kind of thing and follow a policy pi here. Next actions I am not bothered. Next action I am taking from a policy pi, right? That's why these key functions are also kind of this tagged with this pi. So if I just follow policy pi after S prime, right, I will get a value of S prime. So this is basically an MRP now, MRP, because I have fixed the policy pi. Here also it's an MRP. I have fixed the policy pi. You can just compute value of S prime, right? Let me write it properly. Value of S prime here and value of S prime here also, right? Now there can be possible, like all possible kind of S prime. For A1, I can transition to multiple S primes, right? So there can be multiple S double prime, S triple prime from A1 only, and here also from Here also I can have multiple, for A2 I can have multiple possible states. Now for the next part, so let's just write the reward here is R of SA1, right? And here the reward is R of SA2. So Q pi, pi means you are following a policy pi after you are taking an action A. Okay. SA1 is what? What we know? We get a reward R SA1, and then what we are taking? We are kind of taking a probabilistic average of the next thing, right? So probabilistic average means you are transitioning to the next state with a probability. So what is the transition probability? P of SA1 S prime, right, times V of S prime, and you are taking it for all possible transitions. So all possible transition mean you are transitioning through possible like set S prime belongs to set S, set of states. And just to bring in that gamma factor, right, the next state discount, we can multiply it with gamma. That's that equation. So that's yeah, this equation, right? RSA equal to sorry, QSA is equal to RSA plus gamma times S prime SA V of S prime, right? So what does it mean? That you take an action A and then you follow a policy pi. This is the reward you will, this is the kind of return you will get, average return you will get as a Q function for that particular action. Okay. Now see the kind of algorithm. It's very easy. So for all state value policy, the value of the policy pi, you compute this q to be this, right, and compute the new policy pi to be just argmax of q, right, and then take the maximum of q to be the next value. Okay, so why it is next value? See, and this is the greedy improvement basically. So let me write it up, the algorithm. So how we can get, see how we can get value function from Q function, value function from Q function, QSA. So we can just take the optimal value function from Q function, right? So whatever action has the maximum value, I will take that as the next policy. So I will just take max of this, which will give me what is the value function for the next optimal policy, right? Because I am taking max over the actions. So the algorithm has 3 steps: loop through all states, That's one thing. This is the improvement part. Okay, loop through all states. What you will do within it, update this equation, and you have initialized, let's say, all the value functions. So the initializations are, let's say, done here. Q to be initialized with 0, value to be initialized with 0, RP, all these things you have. So R matrix you have, P matrix you have, possible states you have, gamma you have, right? These things you already have. Now loop through all the states, do this update. QSA is equal to RSA plus gamma times P and V, right? V of S. So you can just do this, P of SA S prime and then V of S prime, just sum across S prime belongs to S. This is the update. And now you have a, see, at this point, your initial policy V is equal to 0. So there is no no initial policy required, right? Initial policy gives you value to be 0. Now you update. So now you have a queue function, one first queue function update. So this is the queue function update. Next, you derive two things. One is you update the new value and you update the corresponding policy, right? So new value, I would take the next policy to be greedily, right? To greedily, what will be my next policy? Whatever action has the maximum queue at this point will be my next greedy policy. So next greedy policy, next greedy policy. And see, I am saying greedy policy because I am taking policy based greedily from queue, right? But queue is actually like future proof. It's like considering gamma. It's considering multiple steps, planning of multiple steps, right? So it's not entirely greedy, but my policy computation from queue is greedy. So I will take what? I will take whatever action has the max queue value. So my policy pi improve improve is equal to what? Argmax, argument max over action set of QSA. So I have the improved policy, and this would definitely, so because I'm taking max over this, right? This would definitely have more value than 0. And what would be the value? These two steps are very important. This is where we monotonically improving the value function. So my value improve would be what? I'm taking R max, so value would be max, right? So max across action set of QSA. So this is basically the improvement part, IMP, improvement part. So you are looping through this until your policy converges. So until there is no improvement for the policy. Okay. So you can stop. So you can stop in two ways. Either the policy is halted or you have no improvement in the policy, or your value function has halted. So your value function has converged to some value, right? So you can have two things. You can check whether the pi I and the pi I minus 1 is same or not. If they are same, then stop. This is the stopping criteria. Or you can check whether your value function vi and vi minus 1, and you can take the infinite norm. Okay, infinite norm mean you just take a minus and get a max. That's the infinite norm. What is the maximum difference you have? You can also take kind of L norm. So minus then square, let's say second L and second norm, right? This same vector difference or something like this. Or you can take an L norm, right? So for most of the cases, this infinity norm works best. So what is infinity norm? You uh, take a minus and then you take a max basically. So the infinity norm equation would look like you take the maximum difference between two vectors. So this is infinite norm, INF norm, INF norm is equal to this. So in both cases, if this is equal to I minus 1, stop. Or if this entire quantity, this infinite norm is less than some epsilon value, right? So some epsilon value, why I'm saying some epsilon? So the values converge like this. So the values so let's say this is the optimal value, right? Your value function would converge like this. Okay, so by ensuring that the previous and the current has within some epsilon margin, you are assuring that okay, this value and the next value, right? So what is the kind of difference in value function? Only this part, right? This part epsilon. So if this part has a less than, let's say, 0.0001, then I know that my my curve has flattened out, right? The previous and the current value function doesn't improve that much, so I can stop there. I can stop at this position. Okay, or you can just take whether the policies has not improved. But sometimes policies, so there can be like same policies which have improved value function. So even if your, let's say, if you check vi and v I minus 1 and vi, there is a change, but pi I minus 1 and pi I can be same in in some cases, right? So this is one thing that like if your value function is improving, not necessarily your policy is changing, right? Because you're basically taking a max, right? So argmax can be same, but your max is improving. Okay, so it's better to go with this infinite norm approach. Now let's go with coding. So let's see whether we can solve much larger environments. So our goal is to solve that 95 state environment, right? Which needs like an enormous amount of 10 to the power 47 GB of RAM. If we go with that iteration looping algorithm, right? Our goal would be to solve that whether we can solve that thing or not. Let's implement it first. So you get the algorithm, right? Let's just go over it once again. So what is the entire thing? You compute this Q function for all states. You improve for all states by taking argmax over that Q function. So you take the greedy policy from that Q. And what is the greedy value function for that Q? Just take a max. So argmax and max would give you next improved policy and value function, right? And then you based on that value function, now it becomes the current value function. You improve the Q again, take improvement from policy and value again, and you just continue looping through this improvement rounds until the policy is saturated or your value function is saturated. Okay, and by this there is a guarantee, and the guarantee proof is here. So the proof reads like this, that this equation, right? This equation, if you just spell it out, right, it's basically an Bellman operator. Okay, and it's been proved. So the proof is long. Okay, so just to sum it up, this Bellman equation, the Q is updated through an Bellman equation over Vs, and it is shown that these Bellman equations are contraction operators. Okay, so this so contraction, what are the contraction operators? So the optimal value function and the value function you are currently having, right? If you just apply that same equation, Bellman equation, multiple Bellman operator multiple time, the the optimal value function would not change, but the value function that you have, the suboptimal one, would their distance would be minimized as you go on applying that equation. So if my optimal value function is not changing, right, then my and their distance is minimizing with time. So at the end, there has to be like kind of converging with each other, right? So it's kind of proof. So it's a kind of formal proof. So you can read the entire proof. I can give you resources on that. But the entire proof is that there is a kind of guarantee that the value function would converge to the optimal value function, and it would bring and kind of your monotonic policy improvement. So it will, because the distance, the probabilistically the distance would keep on minimizing after applying the Bellman function, right? Bellman operator. So it will give you a monotonic policy improvement. Now let's go to code, how we can implement it. Right, okay, guys are with me. Fine. So just interrupt me if you just find anything confusing at any point. Okay, it's better to, yeah. So to go over another two. It's called policy iteration. Yeah, this is the value iteration. Okay, so let's just only copy the kind of algorithm part. Okay, this is the algorithm part we have copied. Okay. Yeah, so this is the algorithm. So what we are doing, we are setting pi as none. So currently pi doesn't have any value. We are putting v to be zeros, right? And v previous to be one. So at this point, this v previous to be ones means this thing would not kind of go. So if it is both as zeros, right, then the while loop would not start. It would not even start. So so setting this up guarantees that my while loop will start, right? And then I to be zero, I means how many iterations it took, right? Earlier, my iterations was really big. It was how much? It was this many iterations we took, right? 10 lakh something, 10 lakh 48,000 something iteration we took to get the optimal policy to be this, right? Now here also we are like saving the value function, improved value function over iterations so that we can plot it out, right? So that we can see, okay, my value function is actually monotonically improving. And this is the infinite norm, sin f norm, v minus v prime, epsilon 1 minus gamma 2. So this is kind of an theoretical bound. Okay, so the theoretical bound for measuring whether the two like current value function and the previous value function is converged is if it is less than 1 minus gamma divided by 2 gamma into epsilon. So that's kind of a theoretical bound. Okay, and it is kind of written in the theory of this value iteration algorithm. Now what you are doing, you are copying v previous to be v copy, right? Updating the q function qsa to be reward function gamma, and then matrix multiplication of p and v, right? And then we are taking v. Now this is the improvement part, right? This is updating value function for each state, is the entire matrix, right? Now this is the improvement, and you are taking, I guess you can see the code, right? I can zoom in a bit. Yeah, and then I'm improving the value, and then the corresponding policies. This is basically take greedy improvement on q, right? You just take arguments, and here also take greedy uh, value of next policy. You take the maximum value from q. So whatever action has the maximum value, q value, you take that action, and corresponding q value would become the value for that state, right? Yeah, now this part is not necessary, saving all this, not necessary. We are saving this value function infinite norm, fine. Let's just also import infinite norm. It's within that helper function. Helper, sorry, helper. Is that infinite norm here, right? Yeah, so we have infinite norm now. And see, it is actually taking absolute and then max, right? Now, if I run this, how many iteration I will take from the same environment, right? I just run it. Yeah, gamma is not defined. It's just defined gamma here. What was the gamma we defined earlier? Gamma to be 0.9, right? So 0.9. Okay, done. See, it just converts instantly for its instant. So what is the I? It takes only 160 iteration. 160 iteration in respect to this 10 lakh something. And what is the maximum value that you get? Uh, let's just take max over the entire value set, right? Yeah, this is the maximum value you get. So 999, right? Earlier we get a maximum value similar to 800. So you can have more value function if I just go with this approach. And this kind of one, you take this max, right? So there is this maximization bias you can have So your this value function can be a bit biased, but it's fine. So if I just plot the value function, right? Wait, I can plot the value function. It looks like this. Yeah. So it's kind of an probabilistically monotonically improving function. Hmm. Oh, sorry, not V. Sorry, not V. V values, right? That's yeah. See, this is how it gets converged. Okay. And what is our policy? Phi. Phi is our policy. Phi. Right. This is the improved policy. Earlier, what we have? Earlier we have this policy. Let's see whether they are same or not. And 0 1 1 1 2 1 0 0 0 3 exactly same. Right now, if I just do play environment dot play as human and with pass this policy pi, right? Yeah, I have the same policy. Go right, down, down, left, down, down, right. And if I spawn here, I can just go and up. So you see the difference, right? The difference is instead of 10 lakh iteration and looping through all possible value functions, we can complete it within 160 iteration. That's the efficiency. So efficiency is around 160 divided by 10 lakh. So let's just copy that. How much fraction of compute you need? You can just get it here. Yeah. So it's actually requiring 0.0001 fraction of the computation of the previous algorithm to reach to the same policy. Now with this, whether we can solve a 96 environment, 96 state environment, right? Let's go with something that we cannot even solve with the previous algorithm, right? So what is the world? This was the world, right? Let's copy it, paste it here, remove this. Yeah, this is the 96 state environment. No, sorry, 95 state environment. Now done. I can see what is the number of states here. State count 95. Okay. Now TQDM I can place it here. Um, Let me TQDM custom in while loop. No, we cannot do a TQDM here, right? Because we don't know how many loops it will take. So we don't know the upper bound, right? How many loops it will take. So doing a TQDM doesn't make sense because the percentage bar I cannot compute, right? There is no progress bar that I can do. It's kind of a convergence thing. So probabilistically it should converge within very fast number of rounds. But earlier we had this upper bound, right? We are looping through all possible policies. So I know that there will be 10 lakh policies. So I can do a TQDM or a progress bar. Here, progress bar doesn't make sense. So now let's run the algorithm and let's see how many iterations it took. Run. It's completed. So it took less than, I guess, one blink of an eye. Okay. And it took 160 iterations. So is that everything is fine or is this? Let me just rerun it again. Okay. I even cannot believe that whether like only 160 iteration can solve this big of an thing. Okay. Save, fine, none. Okay. Done. 160 iterations only. And the maximum value is same. Plot PLT. Maybe I am doing something wrong. It should not be this fast. Net plot lib dot py plot as PLT. I can do something like this. Yeah, I think we are fine. So pi is like this. I can. Okay, now see. Let's follow follow from any four states, right? Right, down, 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 right, up, left. We can reach. Fine. Now let's go to any other possible states. Let's go to something like here, right? Now down, left, down, 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 right, up, left. We can reach it. Now go to any other possible states. Let's say if I start from here, right? Down, right, up, right, up, left. Yeah, we can solve it from any state to any state. Okay, so you can kind of get the power, like how much powerful this algorithm is, right? Then it's very easy. So what you are doing, you are updating q values for each state, then you are taking an improvement on the next value and taking an improvement on the next policy with respect to a greedy update, right? You take the maximum value there is in the q function, you take the maximum, like whichever action has the maximum value, that to be the next policy, and based on that update the q function again, update the same policy and value again, and you do this thing until you kind of converts the value function. Okay, let's go for another, like something more bigger environment, right? And you'll see how quickly you can solve it. Let's just ask ChatGPT to give us a kind of good challenging environment to solve, right? With this query that, okay, I can define a grid world like this. Give me with W to be wall, A to be agent, O to be obstacle, and G to be goal. Give me a challenging, let's say 200, or no, not 200. Let's say give me a challenging 150 state environment. Okay, that should be my query. So I can define a uh, grid world like the above pattern. W to be wall, A to be agent, and O to be obstacle. Give me a challenging 150 state. Define a 95 state grid world like this, one state uh, grid world. Yeah, it gives me a challenging. I think that is the goal. Can you see the goal? I cannot see the goal here. G. Oh, goal I have not mentioned. Okay, we mentioned it here. To be A, O to be obstacle, and G to be goal. It world having a valid path from agent to goal. Having a valid, not multiple valid paths from, just to make sure that my world is solvable, right? Uh, okay, it puts goal here only. Just let's just put somewhere far, right? Uh, put the goal somewhere far from the agent. Okay, now it has, oh, okay, all those things are goals. Now anyway, let's just take the previous one and we can just move the goal according to our requirement. Okay, so now not this world. My world is this. Let's not keep it here. Let's keep the goal here, right? Let's keep it here. Let's see whether we can solve it by looking into it. It's a 65 state. So I think it is hard for ChatGPT to understand what we are doing. Envy.play as human. And my state currently looks like this. It's good actually, right? We can reach it. It's much kind of looks like a maze, right? It's we can reach it like this. And any other places also. You can if my mouse is here, let's say if my mouse is here, right? Here, right? Then it has to find this way, this entire way to reach here, right? Okay, it's a really interesting environment that ChatGPT has, and it's also challenging, right? Very challenging from the previous. It's very kind of shallow. We can reach the goal very quickly with the previous environment, right? But here we have lot of kind of obstacles and ways to find, right? It's good. So let's restart and not play as human. Now run. Takes same 160 iteration, same value function, like similar 160 iteration, it converts to the same like value function. Yeah, the policy looks like this. If I just plot the policy, right? Yeah, it's like this. Now let's see. There are some points where it is failing. See, if I just go from the start, right? Left, right, left, right. I can reach. Fine. From where I cannot reach. See, this is an kind of failing policy, right? If I just go right, I'll die. This is one bug we get from the policy. It should be left, right? So we might keep the policy improving for some more amount of time. Let me like reduce that epsilon a bit. We'll get a improved policy. Okay, now and see, it's only one thing that is faulty, right? No, there are multiple places where it has fault. So here, right here, it can go to this thing. So this spike is there. It just go and fall into the spike, right? So these are like this part, entire part is suboptimal. This should be right. But other things whether we can reach this entire part cannot be solved because it's kind of an yeah, I just opened this thing, it will be solved anyway. This part cannot be solved. Here it is fine. We cannot solve anything through this loop. Yeah, okay, but let's just see where are the problems. Here is one problem, here is one problem, and anywhere else this part cannot be solved, this part cannot be solved. So two problems we can see. One is here, one is here, right? This should be solved. We just go and change the epsilon value. Instead of this, we can have, let's say, to the power -5. Okay, more. Go for a kind of allow more policy updates. That's what it will do. Let's just restart. See whether we can still it take 182 iterations. So there are, I guess, how many new updates? So it is allowing 60 to 82, means 22 more updates, right? From the previous one. The value is fine. Let's see whether those positions has been fixed or not. No, no, those positions are not fixed. But anyway, my kind of policy is successful most of the places, except some places like here and here. Let's see whether I can go with lesser epsilon or more gamma. Actually, more gamma would help, right? Let's go with 99. So when we are looking into 100 next steps instead of 10 steps. Okay. So run, run. It now takes, because we are taking 0.99 gamma, it takes 2000 iterations to convert with a epsilon value of 1 e to the power minus 4. Now, what is the maximum value that we get? That's fine, because we are, it's 10 times more, right? Because we are taking, instead of 10 steps, we are taking 100 steps now into consideration. Now it's fine. So let's see whether we have solved that issue or not. Can we? No, still we cannot solve the issue. But it's fine. We can solve the grid mostly in most of the places except this part and this part. Okay, so let's just change the environment a bit. Let's see whether we can solve it. Let's just remove this obstacle from here and open up a web opening from here. Okay, now let's see what will be this next state. Run. Now it is still here. We have some problem. This part is solved. This part is solved again. This part has some issue. But like anywhere else except this part is solved, right? Mm. So if my mouse somehow reaches to this state, to this two state, right? Then it directly goes to here. Okay, so you get the point, right? So there are in most of the places, let's say if my mouse starts here only, so it can go follow this entire path and reach to the cake, right? If my mouse starts here, it goes here and then it falls to that obstacle, right? Okay. And if it starts here also, it falls to the obstacle. Okay. And if it starts here, it goes, yeah, it reaches here. Fine. Okay. Yeah. So this entire path becomes faulty. This entire part becomes faulty. Other than that, my whole space has been kind of, this policy is kind of fine. Let's go with more 9996. Why that two states are not changing? If these two states get changed, then everything is fine. Okay, leave it. Let's go with another word. Give me another grid word. But you get the idea, right? It can solve most of the grid, but for some parts it is not possible to solve word. Uh, the grid should be closed on all sides with walls. And now it gives me this type of an world. Okay, let's see what it should look like, whether it is even solvable or not. How many state we have? 66 state. Is it solvable? There is this path to reach. Fine. And my start state is this. We'll only see from the start state for now. Solvable. Fine. Let's just keep gamma to be 0.9 and this to be 0.4 for now. Just to, yeah, 160 to the 10. Fine. Okay, let's see. Down, down, right, 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 down, 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 right, 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 down, right, right, right. Fine, we can solve. Any other place? Here we cannot solve it. We have to just look, go from this area to like this, but it cannot somehow cannot get it. Uh, 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 mhm. Okay, but from starting state to some others, like few other states where there can be a reachable path, right? It can solve it. So for example, here we can solve it till end, but these states are these states cannot be solved, right? So I guess we have to increase the gamma parameter for this because see, it is more than 10 states away from these states, right? So it's actually not getting this reward signal from up here. So it's so which action I should take, right? So I am only taking decision based on next 10 steps. So these ones are actually not getting the kind of signal that it can get from reward. So let's just increase gamma and see whether we can solve for this ones. You say 100 steps. Fine. No, no, we can still solve it for the starting state, right? But for other states, we cannot really solve it. Anyway, so this is the kind of policy like value iteration algorithm we have. Okay, okay, the okay. So one possible problem that we can have, see this behavior. Why we are seeing this behavior? It's very crucial. My game would end, right? Or it will not end actually. It will get a minus and minus 10 or something reward if I go with this path. Okay, let me check how much reward I will get. Uh, if it is, it's actually because of the reward function. Uh, Gridworld modules, whole, right? Step function, uh, response reward, response agent move, agent, press the agent class, agent, then move. Right. See, this is the reward we have. If it's a goal, give a +2. If it is a whole, give a -2. It's a normal state, then give a +1. If it is an unknown step, no, 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 no. It's state symbol. State symbol, move, right? Where's the reward function that is defined? It's because of the reward function. I can leave that. Wait, let me check. RSA, self dot build model. What is that build model function? Yeah, build model. Next state reward. Agent dot move, next state reward. Agent dot move, next state, next state. Okay, got it. So there is this. Here, see, if it is a goal state, it is plus 100. If it is a whole state, it is minus 100. Okay. Otherwise, it is a block state. So you are otherwise it is a minus 1. That's it. Okay. So what is happening? So it is getting a minus 100 here, right? And a plus 100 here. So they be cancelled out. And now here it gets a minus something. Hmm. This should not happen. So this local kind of distortion that we have, it should not actually happen, because see, if I take this path, entire path, plus 100, right? It is a positive quantity. Whereas if I go with this path, so I will fall into here. So it's minus 100. This is plus 100. It's 0. And then I have a minus some 10, 15 something, right? 2Ds here. It should not usually take this path. But anyway, somehow it is taking it. Maybe it is due to that we are not considering our environment to be terminal. So it is not actually terminating at this point. You have to see, you have to kind of deeply analyze it later on. Okay. Uh, Let's see whether our algorithm has something to do with it. PAP. Nope, all fine. 68. It is still taking this path through the obstacle. Okay, so we can get it. So the problem with this value iteration method is it can solve environments which are not too complex. So if I can just go with the previous one, right? If I can just go with a less complex environment but with more states, that is this 95 state environment, right? It is less complex but it has more states instead of this highly complex environment. I can solve it from all possible states. This is kind of a less um, like less complex environment, rather less larger, right? Yeah, we can just solve it, yeah, from all possible states. See, we are not falling into these no, we can fall into these things here, but most of the time we are avoiding it, right? So the problem with value iteration is there can be local areas where the policy kind of fails. Okay, so the next algorithm, so this is the part of this is kind of the last part of your model based algorithms. Okay, so when you have with this PSAS, and RSA model of the world, reward system and the dynamic system. Later on, we considered that the model is too hard to compute, so we can directly interact with the world instead of, I guess up till here we have it. Okay, we can directly interact with the world and get the, yeah, this ended. Yeah, that's part of model free reinforcement. Okay, so two things we can kind of keep in mind. One is this, so if I loop through all the possible policies, it is not feasible always, right? Because because of the possible combinations, the space required to store those policies are very big. So we have to somehow improve from a suboptimal policy to the next, like somewhat more optimal policy, right? That's when this value iteration comes in, and it can converge quickly. However, it can has local suboptimalities. Okay. So for example, here, right, if I start from here, I can just go and fall into this obstacle, right? Maybe we can solve it if I can just have some sleep in the environment. So sleep to be, let's keep sleep to be 0.2. Let's see whether we can solve it now. No, still we can have similar type of uh, glitches, right? Okay. So that's the problem with value iteration. You can solve it really quickly with monotonic improvement in policies. However, it might struggle in some local areas and just fall, then give a suboptimal policy there. Okay. So now the next phase would be going for that your model free reinforcement, where you, what you are doing, you are taking actions on the environment itself, getting those trajectories one by another. So you start from a starting state or a set of starting states, and you keep taking action based on your current policy until you reach the terminal state, or let's say a timestamp gets ended, right? You can, so it can be it can be possible that you are only allowed to take 100 actions, and then the game closed, right? Just like what we do for this uh, your Lego games, right? You can have only certain possible number of actions. After that, your game ends. So whatever maximum reward you collect within that period, that will be your game's reward, total reward, right? So you just go sample multiple such episodes and update your policy based on those experience. And then after you improved your policy, you can go again and take some more experience with the environment, and then just update your policy based on that experience again. So those are known as model free policies. Okay, model free algorithms. Here we already studied up to model based. So when we have the PSA, PSAS and the RSA matrix. Okay, you can go check, like kind of play with these algorithms, right? You can easily compute this PSA and RSA matrix from any grid world, right? Using the library. You just have to provide the kind of a valid uh, world representation. Okay. Now, I guess next class we can kind of discuss the questions from week 11 and week 12, right? And covered some algorithms for model free reinforcement. Okay. Okay. Do you have any questions at this point? So next class we will do like practice the questions from assignment 11 and sorry, assignment 10 and 11, right? And also discuss some other algorithms for model free reinforcement. When we don't have the matrices for PSAs and RSA, instead we just interact with the world in a loop, right? Take actions based on the current state and update our policy accordingly. Yeah, in the exam, MCQs only come. So I guess someone also posted in that group chat, right? That let me just read it. Uh, It's so many messages after that. Okay. Yeah. So yeah, so most of them are there should be three sections, right? A, B, and C. A having 10 questions, B having 20 questions, and C having 20 questions, right? And all are 2 mark questions. And the questions can be MCQs or small code snippets. uh, some small codes like calling library. So there should be some small code snippets just to fill up. You have to just, let's say, fill in the blanks or uh, something like that. Okay. And your most of the questions will be MCQs. Okay. And it's a kind of online test. So, and a calculator should be also available. No, no code as such, because there, I don't think there will be any like your IDE support with that in coding, with that exam environment. But you can expect small code snippets and you have to fill out some part of that snippet. So it should be like this. So you are, so for example, like this, right? You have to import linear regression from scikit-learn. Option A, from scikit-learn dot models import linear regression. From scikit-learn, second, option B, from scikit-learn dot linear models import logistic, or right, something like this. You have to check which import is correct. Okay, or let's say you have to compute uh, let's say L2 norm, right? And then there can be 3 code snippets or 4 code snippets which are computing L2 norm. We have to click which one is right, something like this. Okay, but no code as such. I don't think so. Okay, just try to kind of memorize which models are from, like, stored in which path of which library, right? This should be kind of enough to kind of solve the snippets, code snippets problems. And mostly it will be MCQs. So focus on theory part, I would say. Okay. And there should be some numericals too. So for example, a data set can be given for multiple options to be selected where there is part marks. Yeah, I don't know what policy they will take. I guess if you choose, so the I guess if you choose all the correct answers, then you will get a marks. Otherwise, you will not, right? Because these are not computer checked most of the times. These are not manually checked. These are mostly computerized checks, right? So either they will put some partial marking policy, or they will just mark it binary. So if somebody checks all the correct options for a multiple select question, they will get marked or not. Something like this. Theory content. Okay. Have you theory content is from someone which that's an exam? Yeah, questions. Uh, so the kind of questions that you can expect is same level as your assignments. Okay. So I have uploaded. So let me check how much I have uploaded from the type PDF, previous questions, right? So I have uploaded till week 9. Let me upload week 10 also. Previous year questions, week 10. I will upload week 11 and 12 in time, right? Because you have deadlines. Just upload it after the deadlines are over. Okay. So up to week 10, you can see what were the questions from previous year also. So this year questions as well as previous year's questions. You can practice them. That would be like more like kind of well enough for the exams. And also the numericals are important. So for example, there is a table is, let's say a data set is given, you have to write a kind of entry. What will be the entry of, let's say, on that data set, something like this, or what will be the first split, whether it will split on feature a value v1 or not, something like this, which split it will take for the first node. Or let's say you are you can be also given to compute entropy for a particular split, right? Or a Gini index for a particular split, something like this. These things can be done. So yeah, also the kind of Bayes theorem questions, right? There can be a lot of numericals upon Bayes theorem. So a simple question would be, for example, you have uh, two baskets, and the baskets have four red balls, five black balls, and the second one has three red balls, 10 black balls, right? And then you have to compute the probability of choosing basket B if you have picked, given that you have picked red ball, right? This type of probability questions can come. Okay, or that thing. Let's say a graph is given, a kind of Bayes network is given. You have to compute a kind of joint probability of, let's say, two events, A intersection B. You have to compute. Then you can just follow through that Bayesian network and kind of compute all or kind of dependent events, right? And multiply them together. Or kind of if you have two kind of OR events, right? If you have two branches, then you can just sum both of their probabilities like this. Just try to practice the questions on Bayesian networks and Bayes theorem. There can be multiple numericals from there. So it's not like you have to do it within that question, right? You have to just select the answer. Even if it is an MCQ, you have to compute it, right? Let's say over your rough paper or somewhere. Just try to do some numerical something. Okay. So I would say going over the assignment questions and the previous year assignment questions would give you a good idea what to expect from the last, like, final exam. In my drive, unable to see the required folder. Please share it with me. So it's, I don't have to share it actually. It's, let me, anyone with this link can view, can have this drive, right? Here you have all the slides, all the codes, previous year questions, or any other slides that I'm using from, let's say, the Stanford slides, right? So they are all put there. Okay, guys. So let's meet next week. Next week we have two consecutive sessions. So from yeah, from Friday we have a session. That's the extra session we have. That then in that session we'll mostly solve questions from week 10 and week 11. And there is this last session too, which we cover the remaining part of reinforcement, model free reinforcement. Okay, so up to TD learning you have in your syllabus. So next we have, I guess, one algorithm called uh, your policy evaluation, something like this, with interactions, anything. And the second thing is this TD learning. Up to that part you have in your syllabus. Then you will stop for reinforcement. Okay. No, I have to see for 26. I don't know the date. Let me. It should be confirmed by the NPTEL coordinators, right? Uh, It should be confirmed by the NPTEL coordinator. So just yeah, all tickets yet to come. Yes. Just see. It should be either announced in the course page, or you will get a mail regarding which date is the exam. Yeah. But I don't have a like clear idea when it is. Okay. So let's close the call. Let's meet next week. Okay. Yeah. Thank you. Please stop recording.